or the gradient effect. Okay, so this one is called K gradient. And it doesn't depend upon the material properties, it's only a function of size, cross-sectional size. K surface depends upon SUT. I told you, ultimate tensile strength. Okay, and surface finish. Okay, this is the second effect. So now we have changed the original one. We now have K gradient, K surface. Okay, so very good. Then the third thing is called the load effect. What if you are not doing axial load? What if you are doing bending load? I'm sorry, what if you are not doing a bending? What if you are doing an axial push-pull? So instead of doing this, you're going to do this. Now what happens? You can see that there is no size effect if it is push-pull. The problem is everywhere things are high. This will drop your strength by quite a bit. Typically for load effect, K load, if it is axial loading, the effect will be 0.85. It will drop it by 85%. I mean, to 85% of its strength. If it is torsional, it will drop it to 59%. If it's bending, of course, that's the ideal one, right? But now it's torsion, this, that, and the other. This is a very complicated thing, so it's a kind of a messy thing. If on the other hand you have torsion plus bending and all of that, you have to do the effect for each of them. So we will deal with that when we get to this K load. So the last one is K temperature. Now this is one of the few things where if it is a hot object, fatigue will be less important. Think of it this way. When it gets colder, the material becomes more brittle, more prone to fatigue. If it is hotter, it will be less prone to fatigue, it will be more forgiving. So generally speaking, at higher temperatures, you will find that this will be beneficial. Okay, let's fix this. It will be beneficial. You get what I mean? So the net thing is the following. Our total SE prime, the actual load is K temperature, K load, K size, K surface times SE prime. So I got to multiply it by 4 factors. The first one is due to surface finish, the second one is due to size, third one is due to load. This time, if it is compound load, we do it separately. That means if it is combination of bending and torsion and all of that, we do it separately. Okay, and then there's a temperature effect. If you multiply all of this, you will get the actual what is that? Endurance limit. Okay, so now let's see how to find these things. And these are completely empirical formulas. Don't ask me why they are there this way. What it is that it's a lot of brutal work by a lot of people. I mean, we are talking from 1850 to about 1900. I mean to about 1950. 100 years of work. Okay, so let's look at an example problem, and then you will see how this thing works. So I'm going to close this up if I can. And here is the example problem. Okay, this is actually directly from the book. It says, estimate the endurance limit of a 32 mm diameter rod of AISI 1035 steel having a machined finish and heat treated to a tensile strength of 710 megapascals. So that's our target. What I'm going to do is I have a nice little Excel program that will compute everything, because I don't want to sit and look up the graph because you can't see it. So I have all of them nicely written up. So here it is. Okay, and for each of them, so we start out by saying, okay, I'm going to choose SI units and I need my ultimate tensile strength, which is 710 megapascals. By the way, the most important item is the ultimate tensile strength. I don't really care about the yield strength. So right now I can even put 0. I don't care. So the first thing is to find out SE prime, and we know how to do that, right? It's half the yield strength until 1400 megapascals. After that, it is 750. So it's actually after that it is 700 megapascals. So in this particular case, it is half of this. So that's why it is 355. Okay. So now we're going to do the modification factors. The first one is surface modification factor. What are the kinds of things that we can do? We have ground finish, machined or cold rolled, hot rolled, or as forged. Can you see that? Those are the 4 items. So let us go back and check what we wanted. Can you see it's saying machined finish? So I'm going to go back here and I'm going to pick machined finish. So this is actually directly from the text. This is one of the tables in the text, and it says for ground finish. So the equation looks like this, and in the text it's called Ka. See, the problem is the way Shigley writes it. They don't tell you what these factors are. They just call it Ka, Kb, and it's hard for you to remember. But I call it K surface. Okay, so K surface is A times ultimate tensile strength to the B. So you can look up machined and cold drawn. A is 4.51 and B is minus 2.65. I mean, don't ask me where I got it. There's some bizarre stuff where thousands of tests were done and they compared it. Okay. So what happens is I immediately get K surface for this is 0.79. Can you see? It's only 79, 80% of the original load. Very good. Now let's look at the size. So size effect, that's the next one. K gradient or K size. The size of this sample, let's go and see. It says 32 mm diameter rod. So I'm going to go back up here and I'm going to change it to 32. And the load type is bending. Okay, so immediately you get that because of the fact that the sample is much larger than the original, than the test one, you will find that its strength will go down by 0.855. Temperature is room temperature. So I'm going to put 25 degrees centigrade. And it will turn out to be slightly more than 1. In this case, it's 1.009. Okay, this is K temperature. By the way, the size effect, the surface modification effect is equation 619. The size effect formula is given in equation 620 and 621. Okay, and for size effect, you have to tell me which kind of loading. So if I made it axial loading, size effect is 1. If I made it bending, size effect is 0.855. Why is axial loading size effect 1? Size doesn't matter for axial load. Same cross section, same load, so nothing matters. Okay, temperature 25 degrees. So that's the temperature effect. Loading there. Bending is 1, axial is 0.85, torsion is 0.89. This is equation 626. So you do that and you'll get 1.0019, bending is 1, and your final modified endurance limit is 240 megapascals. Think about it this way. If it were an ideal specimen, it was 355 megapascals. Because of the fact that it's a machined surface, which is 32 mm in diameter and at 25 degrees centigrade, and it's under bending, it turns out to be 240. 241. Can you see? It's 240.9996. You got the idea, right? So there are 4 effects that you have to worry about. Surface, size, temperature, and load effect. You multiply all of that, you will get the endurance limit. Thank you.